All right, so if we go back to where we were on Friday, we started classifying matter by phase. Now, again, if you're in Friday's lecture, you have all of these notes already. This was the last bits of Friday. And so remember, we talked about classification based on phase. We also talked about classification based on substance in terms of, is it a pure substance or is it a mixture? And so we ended talking about elements and the difference between elements and compounds in terms of what their composition actually is and what it is not. So remember, with elements, we're talking about one specific type of substance. For compounds, we're talking about two different types of atoms that are chemically combined in some kind of way with each other. And that's really what the difference between the two is. Chemically, they're the same in terms of all elements, all atoms of a given type of element are the same. All molecules of a given compound are the same. But what separates the two from each other is how many different types of elements are present. A compound, I have to have two different elements at minimum. Element, I'm just going to have the one different kind. And we talked about mixtures. Mixtures fall into two different categories as well. We have the homogeneous mixture, which we call a solution, and we have the heterogeneous mixture. And the main difference between them is in their appearance. Homogeneous mixtures are homogeneous. They look the same. So think of things like your Powerade, this ever so handy sanitizer. If I pour this into a bottle or a cup or something I can see, I'm not going to find the alkyl dimethyl benzyl ammonium chloride, the alkyl dimethyl ethyl benzyl ammonium chloride, and all of the 99.98 other % of this stuff, which is mostly water, and probably some sort of alcohol or dispersant. I'm not going to see any of that. I'm just going to see one uniform solution. It's going to look like that guy's water over there, Peter, right? So that's what a homogeneous mixture is, a solution. Even the water that we drink is a solution, because very rarely, unless you buy distilled water and drink that, most water has something that's added to it. Minerals, calcium, depending upon where you live, if you have well water or nearby you get municipal water, you're going to have other dissolved substances in that as well. It's not a pure solution. The only way to get pure water is if you basically distill it. You boil it off and you collect the vapor as it evaporates. So those are all solutions, and they're all uniform, homogeneous. Whereas heterogeneous solutions are the opposite. We know that there are multiple components there because we can see them. Just open it. All right, come on in. So I can see every component in a heterogeneous solution or a heterogeneous mixture, and that's because they are present. They're literally easy to pick out, easy to see. And so what I've composed here is a flow chart of sorts. What we can do in looking at this particular flow chart is we can associate certain kinds of things and answer questions and help to devise what kind of solution we're dealing with, what kind of substance we're dealing with, based on the answer to those questions. And so the first question we might ask is, let's say I'm given a substance. does this have a uniform composition? Well, without knowing the makeup, probably going to be difficult to tell. But if I have a substance like again, our sanitizer, I can look at it and say, okay, this has at least 3 ingredients, 3 unique ingredients. So no, the composition of this is not uniform in terms of not every molecule in this looks exactly the same. I'm told that there are at least 2 different active ingredients that are different from each other. That would push me into the mixtures department. And then based upon its appearance, I could classify it as a solution or as a heterogeneous mixture. But if it was pure, if it did have a uniform composition, let's say that it was just the alkyl dimethyl benzyl ammonium chloride, and that was all that was in this bottle, then we would say definitely, okay, this has a uniform composition. I go down here. How many types of atoms are there? Well, let's see. Bottle says that there are carbons, hydrogens, nitrogens, and chlorines. Okay, well, that's not one type of atom. That's multiple types of atoms. So I'm dealing with a compound there. So based upon your answers to these questions, you can start to kind of break things down and classify based upon this idea of composition. And so this is really the first kind of fundamental concept that we have here from a chemical standpoint here in this class. Took us over 2 weeks to get here. But we're finally getting into a little bit of what we would actually call chemistry, as opposed to just physical science or just science in general. All right? Any questions about matter before we move on? Yes?
Was there 3 states of matter?
Yes, there are 3 states of matter.
Can you tell me what they are again?
The solid, the liquid, and the gas. Now, I said on Friday, some of you probably have heard of a 4th state, plasma. You might have heard of things like plasma torches or things of that nature. We're not going to talk a whole lot about that. Plasma is basically hot ionized gas, and we only can create it artificially in very small amounts for those kinds of torches. Where we see it the most often are things like in stars. So like the sun has a good bit of plasma in it. Other stellar objects have plasma in them. Aside from those, we don't see it a whole lot. And so we're not going to talk about it much. All right, so based on our understanding of matter, a couple of questions here. I want you to think about this, and instead of A, B, C, D, we're going to give this the old 1, 2, 3, 4. So think about this question. Flash up a number of fingers, 1, 2, 3, or 4. Tell me what you think. Which of these substances is not a pure substance? Okay, I'm seeing a lot of 2s, a lot of 4s. All right, so somebody tell me what a pure substance is. What is the qualification for something being a pure substance? What does it have to have?
Uniform composition.
A uniform composition, what does that mean?
Like it has the same exact type of molecules in it.
Okay, correct. It has to have a uniform makeup. I look at every single molecule in the sample, and all of those molecules look the same. What's the chemical formula for water?
H2O.
Okay, does that vary? Can it be H2O2? Can it be H3O? No. Okay. That is what we mean by uniform composition. When I say water, you say H2O because that's the only combination of hydrogen and oxygen that makes water. That's a purity. So water, we can eliminate from the list. Carbon dioxide. What's the chemical formula for carbon dioxide? CO2. Does it vary? No, it's always CO2. So same thing. What about carbon? Carbon is C. It doesn't change either. Okay, what about air makes air an impure substance? Yeah, we've got nitrogen, oxygen, carbon dioxide. Those are the three primary components of air. Got other little bits in here and there, depending on where you are. But I've got multiple components. And the air composition can vary from place to place to place. You go into a city where there's a lot of traffic, you're going to get more NOx gases, you're going to get more SOx gases. That's nitrogen oxides and sulfur oxides from the pollution. You go onto a farm, you're going to get, especially a dairy farm or a cattle farm, you're going to get more methane production. Different variations of air composition. You go up into the mountains, the air is thinner. You're going to see just a lower composition overall in terms of each of those components. So air is our impure substance here. All right. Same deal. 1, 2, 3, 4. Solutions can be solids, liquids, gases, or all of those things. All right, again, I'm seeing a lot of 4s and a lot of 2s. Okay, now, if you're thinking liquids, you are correct in the sense that most liquids, or most solutions rather, are in the liquid phase. That's what we tend to think of. Both of the examples I gave, liquid, liquid, liquid. But however, we did just make mention of a gas phase solution. You're sitting in it right now. Look around you. Can I pick out the nitrogen that's in our air? Can I go to the section of the room that's oxygen only so I can go over there and breathe a little bit deeper? No. So gases can be solutions too. Now, what about solids? So if B and C are correct, then D has to be correct. So what would be an example of a solid phase solution? Go ahead.
Can you say like something that's big is a solid solution?
I know where you're coming from, and you could say something along those lines. I was thinking simpler than that, but yes. Now, we gotta be careful because when we bake things, when we cook things, those are chemical reactions that are taking place as well. So the starting ingredients are getting transformed. But yeah, if you bake brownies, so long as you don't put like, nuts or chocolate chips or something in them, the composition by the time the brownies are done baking is pretty uniform. thinking of something else. You know, actually, that's pretty much a compound. It's a polymer compound. Look what you're sitting on. Look what your books are on. What are your tables made out of? Okay, not the wood, but what's holding the wood up? Okay, what kind of metal? Probably steel. Yeah, carbon steel. Alloys, brass, steel, stainless, 14 karat gold. All of those are mixtures of metals that when they get melted together, look uniform. That's an alloy. Alloys are examples of solid phase solutions. Yes, we probably will have to melt them down to the liquid phase to get them to mix together. But when they harden, the results are uniform. I can't look at my rings. My wedding rings are 14 karat gold. I can't look at these and say, okay, this part's the gold, but this part is the titanium, and this part's the whatever else went into the production of it. I can't look at that way, mainly because I can't tell the difference. All right, so let's move on to something a little bit different. Liquids. Now, you did a lab on Friday about solubility, right? You took salt or sugar and you put it in water of different kinds and you saw how well it dissolved or didn't dissolve. That was the lab you were supposed to do. Okay? When we have solids dissolving in liquids, we usually describe that in terms of a characteristic called solubility. The more salt that we can dissolve in water at a given temperature, the greater its solubility rating is. And we didn't ask you to do this, but if I had asked you to take that salt and compare it to, say, calcium chloride salt that gets used for salting roads and sidewalks, at least places other than here, or maybe calcium carbonate, which is used for, not in this room because we don't have blackboards, but chalk. Those would have different amounts of solubility associated with them. But if it's a liquid that we're trying to dissolve in another liquid, we don't use the term solubility often. The term that we use is called miscibility. Liquids are said to be either miscible or immiscible with each other. When we call them miscible, that means that they dissolve very, very well in each other. Common example would be things like alcohol and water. For those of you of the legal drinking age that have gone into a liquor store before, you'll find that there are many, many, many different varieties and concentrations of alcohol and water in said store. Why are there so many varieties? Well, for the obvious intents of alcohol, but also because they can. The solubility limit of alcohol is only 40%, then 80 proof would be as good as it gets. You couldn't get any higher. But the fact of the matter is, we can make solutions of alcohol and water up to 95% alcohol or practically 100% water. That's how soluble those two liquids are in each other. That's how miscible they are. And so on the proofing scale, you can go all the way up to 190 or all the way down to practically zero. Of course, you wouldn't see that zero proof sold anywhere near a liquor store. You'd see it sold at Walmart. But that's what miscibility is. Liquids are infinitely dissolvable in each other, or at least very, very close to infinitely dissolvable in one another. You can actually get down to greater than 95% alcohol, but requires drying agents to do it. And those drying agents are usually not consumable, which is why, again, 190 proof is kind of the limit in that regard. Immiscibility, these are liquids that do not mix together. They do not dissolve in each other. And as a result, they're going to form kind of layers based on their density. This is where our ideas of specific gravity come in. Those that have high specific gravity will sink. Those that have low specific gravity will float. Sometimes we can tell the differences based on color. Sometimes we're just looking for this little tiny line that kind of shows up between the two layers to let us know that they didn't mix. Real easy example of that, oil and water. If you take oil and water or vinegar or anything like that, you'll see that they layer up on each other, and it's usually pretty easy to see. Now, in some circumstances, we can use this kind of separation to our own mutual benefit. So, for example, anybody here watch IndyCar, Formula One? Any of that kind of auto racing? Okay, sometimes there are. Those cars run on a very, very high octane fuel. It's pretty purified methanol usually. And if one of those cars catches on fire, it can be a really big problem. But what they actually do to solve the fire is they just dump water on it. And the water doesn't actually extinguish the fire, like suffocate it like we usually think. What happens is that it basically acts as a gigantic heat sink and dissolves in the methanol and basically lowers the evaporation rate of the methanol and makes it so that it can't be on fire anymore. But other kinds of organic materials aren't quite so lucky. Take, for example, our benzene and our carbon disulfide. Now, if either of these were in a controlled container and on fire, what we would see is that the benzene would not be able to be controlled by water. And the primary reason why, benzene has a lower specific gravity than water does, so it will float on water. And so what happens is you dump the water on top, and instead of suffocating the vapor, it just sinks to the bottom. The fire keeps going up on top. For benzene fires, we would have to use either some kind of a containment system or a foam or some kind of something to ultimately stop that fire. But for carbon disulfide, because carbon sulfide's specific gravity is greater than that of water, it's about 1.27, water will float on top of it. And when water floats on top, it'll basically suffocate the fire by sealing off its access to oxygen. Fire goes out. Now, in both of these cases, we have immiscibility going on. That's why we get this layering to occur. If miscibility was there, it'd be like my alcohol and water example. When IndyCar catches on fire, water is usually used to help dilute the alcohol, which in turn helps to keep it from vaporizing, keep it from spurring out of control. But for immiscible liquids, this is one of the ways that it goes. Now, if the fire was not contained, so these were both occurring in a drum of sorts. If the fire wasn't contained in that way, like say it was running on the ground, this technique wouldn't work very well because spraying water on it would only serve to move the fire instead of containing it. You'd end up with a bigger mess on your hands than this. This moves us into our concept here of energy, though. If you can recall from the very beginning of this chapter, we define chemistry as the study of matter and its interactions. And one of the interactions that come as a result of matter doing things and changing is that energy is either going to be absorbed or released in these processes. By definition, energy is the capacity to do work. So any kind of energy that we describe is able to do, or at least has the potential to do, some form of work on another object or have work done on it by the surroundings. Now, in broad terms, work is just a force that is applied over a distance. So if I take this pen and I push it across my desk, I have applied a force to it, and that force I've applied for as long as I held it provided energy to it to allow it to roll. I can do the same kind of thing by throwing it. Never goes in. It's the same kind of thing though. I've applied a force. That force gets inputted from me to the pen, and the pen flies through the air until gravity eventually acts on it enough that it falls to the ground. Now, in terms of energy types, there are lots. Any textbook, any web resource that you find is going to give you tons of types of energy: mechanical, electrical, nuclear, chemical. But they really all fall into two main categories. There is potential energy. That is stored energy that a substance holds based upon its position or its internal configuration. So take, for example, you have a pocket watch. The pocket watch has within it gears that you have to periodically wind up. Your winding up the watch provides that potential energy for the internal gears of the pocket watch, that as soon as you release it, that spring starts to unwind and turns that potential energy into kinetic energy. Now, kinetic energy is our energy of motion. So that kinetic energy can come in a lot of forms. As I mentioned, the case of the pocket watch, we're turning it into mechanical energy, where the spun spring unwinds, and as it unwinds, it starts to turn the gears inside of the watch to make the watch go. But other kinds of things can also fall in there as well. I threw a pen across the room about a minute ago. It went from potential energy of being in the position of my hand pulled back to kinetic energy as it flew through the room and eventually hit the ground. Now it is sitting there at rest. It is at a certain amount of potential energy based upon where it is currently. If I push it over to a flight of stairs, it can fall down those stairs because it is at a higher position at the top of the stairs than at the bottom of the stairs. Now, as I mentioned before, there are lots of different forms of energy. But again, they all fall into one of those two categories. Radiant energy, the energy that comes from light, heat, and X-rays. This is mostly kinetic energy of some kind. When your body interacts with heat or with X-rays, your individual cells will actually start to move as the energy is transferred from the radiant heat to you. Thermal energy, energy of heat. Stand next to a bonfire, you feel warm. Stand outside in the snow without a coat on, you feel cold. What's happening in each case? The hot object is transferring heat energy to the cold object. In the first case, the bonfire was the hot object and you were the cold object, and so you felt warmer as a result. In the second case, you're the hot object, and Outside is the cold object, and the heat goes out of you to warm up the outside. And it doesn't do a very good job, which is why you feel pretty cold pretty quickly. Acoustical energy, the energy of sound, usually comes once energy has been transferred to another object. You pluck a guitar string, you've introduced kinetic energy to that string as it vibrates. And as it vibrates at that resonant frequency, you hear that as a sound. Mechanical energy, I already talked about that with a watch. Chemical energy, when you do a chemical reaction, we can evaluate the energy that was present before the reaction versus the energy that's present after the reaction. And the difference between the two tells us how much energy was either gained by the chemicals from the surroundings or given to the surroundings by the chemicals as they go through their transformation. And then finally, atomic energy or nuclear energy. This is the energy associated with the atom itself. And most of this is potential energy that will stay as potential energy until we enact some other kind of force on it. Or if the atom is unstable enough, the atom acts as its own unstabilizing force and disintegrates, breaks down. And we'll talk more about that particular kind in about a month. Now, when it comes to chemical energy, we have to understand all matter in all of its forms, regardless of its phase, regardless of its state, is going to contain some amount of chemical energy. Because ultimately, this is the energy that is stored, excuse me, that is stored in the chemical makeup of the substance itself. And again, this could be down into even the nittiest of nitty-gritties, getting down to individual quarks, muons, subatomic particles, or even just the nucleus itself. It has this many protons, this many neutrons, this many electrons. And something about that ratio of those items to each other provides it an inherent amount of chemical energy. Now, this is the chemistry of hazardous materials. So it would be poor design for us to say anything other than when we get into talking about hazardous materials, understand that most of the hazardous nature of those materials comes from their chemical natures, comes from their makeup, their design, something inherent in their composition. And that's why they end up being classified as hazardous, because something in their makeup provides that hazard. Now, when it comes to talking about energy, we often have to phrase things in terms of temperature. And the reason we have to do that is because temperature and energy, especially heat energy, are very closely aligned with each other. Temperature is an indication of internal energy. So when we think of temperature, we need to think about the internal energy of a substance. The other thing that we have to draw out of this is that heat transfers in general are going to occur from a hot object to a cold one. So when we talk about movement of heat energy, we usually think of it in that way. And that's why temperature is so important to the discussion of heat energy. I've got a hot object, I've got a cold object. The hot object is going to warm up the cold object until they reach some sort of state of thermal equilibrium where they're at the same temperature. But temperature itself is not a measurement of heat energy. It's a measure of internal energy. How fast are those molecules in that substance moving? Heat energy is what happens when energy is transferred from one object to another. Now, as far as temperature is concerned, we're probably most familiar with two different temperature scales. Here in the United States, the most common and popular is the Fahrenheit scale. Fahrenheit scale, which for most temperatures on most given days is used for our weather. For example, this morning it was about 30 degrees outside when we were driving in today. There are only a handful of countries that still use the Fahrenheit scale. We talked about the units already. Very few countries use the customary system, and the Fahrenheit scale is part of that customary system. Most other countries use Celsius scale, and there are some issues with that one as well. Both of those are considered relative scales. And what we mean by a relative scale is that it's based on a definition. Now, I say this not because relativity is a bad thing. Every unit that we use is a relative number. We had to start somewhere. We had to define something. Somewhere, someone down the line devised that a foot was going to be about this long, and that an inch was going to be 1/12 of that foot, and that a yard was going to be 3 of these things, and that a mile was going to be 5,280 of these things. If you go into the annals of history, basically every unitary system that exists had to start with definition somewhere. So relative scales are not necessarily a bad thing. But in this case, where we're talking about something that is related to energy, relativity is a little bit problematic because it introduces some interesting kinds of characteristics. If I'm looking at an energy scale, so let's just forecast into the future here. I said it was about 30 degrees today when we came in. If tomorrow morning you wake up to come to class and it's 15 degrees, is it literally twice as cold at 15 than it was at 30? No. And if I came in and it was 60 degrees, would it be literally twice as warm? No. Therein is the problem with an absolute scale. I'm sorry, with a relative scale. I can't tie temperature differences to energy differences on a relative scale. But on an absolute scale, I can. Because the absolute scale only has one definition. And that definition is that if we are at the 0 point of that scale, there is no energy. So the Kelvin scale is our favored scale for that reason. On the Kelvin scale, a 0 value means 0 energy. Means that the molecules literally stop moving. Assuming all else, we can use those differences accordingly. So the difference between 15 Kelvin and 30 Kelvin, well, that is a doubling of energy. And 30 Kelvin to 60 Kelvin, that's a doubling of energy as well. So the Kelvin scale is the scale that is on the SI system as being the base unit. And for that very important reason. Now, offhand here, does anyone know what the definitions are for the Fahrenheit and Celsius scales? Has to do with water. And correct. That is, those two data points are what the Celsius scale is based on. Water freezes at 0, boils at 100. Every other temperature value is kind of a relative guess based on those two values and the energy of them. Fahrenheit, it's even a little bit more sloppy. Old story goes that Fahrenheit had a scale, had a thermometer with 180 tick marks on it. And so he used the bottom of that to define his freezing point and the top of it to define his boiling point. 32 and 212 on the Fahrenheit scale end up being relative to the 100 and 0 on the Celsius. Now, some good news. As far as the Kelvin scale is concerned, we can see that the Celsius scale does follow a similar makeup. A 100-degree difference on the Kelvin scale is the same as a 100-degree difference on the Celsius scale. A 1-degree difference is the same on each. Not quite the same for Fahrenheit.